It's of course a perfect example of lousy performance. First me showing up late and then the computer taking a long time to boot. I might as well get started talking at least. You will hear me talking quite a bit and quite fast as well. I've got too many slides for the session, so showing up late is a very bad idea. Just to warn you, this is really not going to be a technical session. I didn't invite my mother, but I think she could have probably gotten maybe 70% of the presentation. It's not looking at performance from very nearby, it's looking at it from far away. And we're not looking to gain performance improvements in the order of 10% or maybe even 50%. We're looking at orders of magnitude. We're looking at times 10 or times 100 better performance. And for that, you don't sit down and look at the little things, but you have to step away and look at the big things. And that's what we're going to do by the time the computer has started and I've got my slides up. Actually, most of the examples I will be using start out in the real world. And then at some point we'll dive into concepts in an enterprise Java architecture. But most of the things that I'm trying to get across live all around you, especially during conferences like this one, where you have lines everywhere. We have large volumes of, in this case, people to process. The same concepts apply. And actually, I took a few photographs last Friday because they perfectly illustrate the point one of the points I'm trying to make. By now it would be nice to have a few slides. My name is Lucas Jellema. I'm from the Netherlands. That's why the very subtle accent. I live in two worlds really. I spend some time at the Moscone Center for Oracle Open World because I'm doing Oracle development and presenting at Oracle Open World. That's one of the reasons why I'm slightly late. And I'm also attending and presenting sessions at Java 1 because I'm also in that world. And it's really where the two connect. And there are many places where they connect, but especially where they connect at the database level. That's where I typically can sort of bridge the worlds. Well, there we are. Thinking through Java enterprise performance, and it's really about thinking through and performance. And the Java bit in between is to get into the conference. So very brief overview. Well, let's just skip it. Let's save one slide. First, the definition. When you talk about performance and you see an arrow pointing downwards, is that a good thing or a bad thing? Well, it's red. It's probably not a good thing. But when performance goes down, well, when response times goes down, it's good. Well, the next slide says response time went up. So in this case, the performance deteriorated. But it's something that you have to get clear what exactly are we talking about when it's about performance. And it's not just about is the arrow pointing upwards or downwards. It's about expectations. You can really only say that performance is not good if you have defined beforehand what the expectation is, maybe what the service level agreement is. And if you didn't make the expectation, then performance maybe is not good, or the expectation was wrong. That's typically the story I try to sell to the users, of course. Real performance requirements should come from real business requirements. Most businesses I know will say something like, well, response time of a web page on average should be 1.5 seconds, and it may never be longer than 3 seconds, based on nothing really. And of course, in a single page application architecture, what exactly is the load time of a page? Because the page will be there and then you will start refreshing bits and pieces of the page. If the user is not able to work, maybe then there's a wait time involved. If the user is still able to continue to work even though processing takes place in the background, that may be perfectly acceptable performance. So definition is important, and driving the definition from what the business really wants is important too, although we have some feeling for it ourselves, of course. We know that certain types of performance probably isn't acceptable. Theater manager sees this group of lovely ladies and he may think, well, they're happy about the performance. Turns out they're actually not. So again, it's about definitions. So performance, if you're trying to quantify it, and your typical enterprise Java application would have a multi-tier architecture. Let's keep it simple. We have our web tier, the browser, our client tier, We have the JE application server where things happen, and there will be a database. There could be other enterprise services as well. There could be web services involved. Let's keep it simple. The performance as perceived by the user has something to do with wait. User has initiated something, has performed an action, has pushed a button, has entered the field value, and the system goes away. And the user has to wait. And the time that the user has to wait is at least associated with performance. Maybe that's not exactly performance, maybe you have to divide or multiply or whatever, but it's definitely an association there. And what determines the wait time of the user? Well, it's determined by the processing time on each tier. So for the web browser tier, the user has to wait for as long as the web browser is doing things, and as long as the web browser itself is waiting for the lower level tiers to do things, or to wait themselves. And the time that the web browser has to wait for the lower level tier is divided, or is split up, in the time the application server is doing stuff, and the application server is waiting for the database. And of course, there's a network latency in between as well. So that's the entire picture. Even though we haven't exactly defined what performance is, at least we know what the elements are that make up the performance. So performance can be screwed at any level and can be optimized at any level. But of course, if the performance goes down by 1,000% at the database level, tuning for performance at the application server level, where we can maybe achieve a 10% improvement in something that's not all that big to begin with, doesn't make sense. So it's important to realize how is the performance composed, or how is the wait time composed, and where does it make sense to try to improve it. So we could be talking about advanced tuning concepts, and this list is definitely not exhaustive, and most of it isn't even that advanced to begin with. Use string buffer rather than string. That's something we all learned in one of the first Java classes we are taught. It's not like huge performance gains can be had there. Maybe 10 to 100%. 100% is good, but it's only in the final stages of refinement that it really matters. We're looking for performance improvements of orders of magnitude. So not 10 to 100%, but 10 to 100 times improvement. And like I said, that requires to step back a little and to carefully think. And I come up with this term, the ISYITF method, and I did that about a year ago. And I presented this presentation a couple of times, but I didn't prepare for, well, quite some time until I last Sunday looked at the presentation again, and I couldn't remember what the abbreviation is for, or the acronym is for. And it took me, well, maybe an hour and a half. I've been scanning through my email. Somewhere this string must be defined, and it's a bit embarrassing. It stands for "it's staring you right in the face." But it didn't, or I did, but I didn't recognize it. So it's the staring you right in the face performance improvement method. And it's all about, well, the fastest way to perform a task. What's the fastest way to perform a task? Well, actually, that's to not do it at all. Well, you may laugh, but there are quite some tasks that are performed in our application architectures that didn't require doing at all. It may not be easy to find them, but when you start thinking about it, maybe we will be able to find them. This is a very simple example, and again, this is fine-tuning at a fairly low level. This is not good code. Code should have been something like this. If expensive evaluation equals true, evaluates the true, and some flag. In this case, in the red case, we'll always do the evaluation. If the sum flag, which is just a Boolean, is false, then we wouldn't have needed to perform the expensive evaluation. But we have to switch the operands around, and we have to change the operator as well. Like I said, this is still at the fine-tuning level. This is not what we are really looking for. This is another example. You're probably familiar with it. In this case, we always tell our logging procedure to write out a debugging line, and the logging method will say, well, we are currently not at debug level, so we won't write it out after all. But by then, we have already done the result of expensive processing method, and we have taken the performance hit, even though we didn't have to. The better approach here would have been to first check if debug level is enabled, and only then do the expensive processing. But still, fairly low level. Now we are at my mother's level. It's about shopping. What's a good algorithm to describe how to shop for some article? Well, we leave our home, we drive the car to the shop, we walk through the aisles, we get the item, pay at the cash, drive back home, and we are happy. Anyone who doesn't agree that this is an example of a shopping algorithm? We don't have time for discussion, so thank you for going along. If you put it in code, it could be something like this. It's not real code, it's close to real code. Maybe it's, well, it wouldn't compile just like this, but this is the way it could look in code. Okay, you're still with me. Get this week's groceries. That's a shopping list to go through. We have our algorithm to buy an item at the store. Now we have to buy multiple items, so there's the code. We iterate through the list of items that we have to buy, and for each of the items, we invoke the algorithm to buy an item at the store. That's the way we usually code. We have a method, it performs a task, we need the task performed multiple times, so we will invoke the method multiple times. The effect of this, of course, is that we keep driving back and forth to the shop for each individual item. This is where you'll end up. And you may think, well, that's a nice story. I didn't even invent it myself, by the way. It's a nice story, but it doesn't happen in real life. Later on in the presentation, I will show you an example that I encountered 2 weeks ago at a customer, and I thanked them from the bottom of my heart to present me such a perfect example for this presentation. Then I resolved the problem for them. They did exactly this. And to give you a small peek ahead, if you're using object relational mapping frameworks for presenting data in normal web pages, and then you use these same entities for reporting, you quickly end up doing exactly something like this. But we'll return to it. So best of all is to not do it at all. But if you have to do it, at least do it not more often than required. That's with the driving back and forth to the shop, where there's more involved. For example, this is, in the Netherlands at least, I'm not sure if you have something similar, now we're all electronic, we don't use it at all anymore, but this is an inventory of all the addresses and telephone numbers that we regularly use. Instead of going to the telephone directory or the yellow pages every time, the numbers we frequently use, we write down is something like this. You could say it's a cache of telephone numbers, the ones that we frequently use. We don't have to search through the thick book all the time. We can pick it easily in this handy mechanism that breaks down after the children have touched it. Something similar, when you're cooking, you won't drive to the shop for every individual ingredient. It's the same example as we had before, slightly different context. Instead, you will have something like your kitchen store, where there are multiple items that you have bought before and that you can, well, it's not really reuse. It's not the same item you're reusing, but it's the family-sized box that you bought that you can now take something out of, so you don't have to go to the store again. So the store, or your personal cupboard, is like your cache of the things that otherwise you would have had to fetch at the shop. It's like the shop is the database and you have your middle tier cache. Or the shop itself, of course, wouldn't go to their wholesale suppliers for every item that's being bought by a customer. It's the same mechanism, but only at a slightly different level. Don't do anything that you don't have to do. Don't do it more frequently than you have to. And with items that you buy at a shop, they're physical items. You can't just reuse them because they perish at the moment you will use them, or at least the things that you eat. With data, it's much easier to reuse. Data doesn't really perish. It may be no longer fresh, but it won't perish. So in general, you could say something like, if the thing that you need, the data that you need, has been produced before, reuse it before you reproduce it, provided that it's still fresh. That's always the balance, of course, that you have to strike. If it has been shipped before from one tier to the next, reuse instead of reship. If it's no longer there, if it's no longer fresh, then of course you do need to reship, otherwise reuse. And always provided it's still fresh. It's fairly obvious, isn't it? And there are several caching mechanisms, because that's really what I'm talking about, caching mechanisms, that will really help improve performance. Not to reproduce, but to reuse if you have the resources to store and if you have the algorithm to find out if things are still fresh. Many things hardly ever go stale. If you have these things available, then caching, and preferably caching at the highest level, is a perfect way of improving performance. That's really one of the main reasons the NoSQL movement is making such huge gains. And you can call it NoSQL, and it's all grand and an architectural pattern, but using a middle tier cache is not all that spectacular. Or at least there are many implementations of caches readily available to us. Of course, the browser also has a cache, JavaScript memory, JavaScript variables that will live between requests. Even better with the latest generation of browsers, HTML5, the more structured persistence that you have at your disposal in the browser. Even in a database, you have a cache. You can say, well, the database itself is a cache, but there's quite a distinction between having to recalculate a result from the data that's actually living in the data files and perform the query over and over again, versus having something in, for example, the Oracle database is called a materialized view, where the result of a query, some aggregation, is stored for you to reuse until it has grown stale, and then it has to be requeried. So if you use it many times more than it is changed, then a cache is definitely something to consider. And again, the higher level caches are much more useful when it comes to performance than the lower level caches. It's a road. It's an old road, it's a sand road, it's dusty, it's not a very fast road. If you want to improve performance, let's put some tarmac on it. But it isn't going to give you all that much performance. It will clog up all the same. To really boost performance with this road, we have to go parallel. Putting tarmac may improve the performance of the road by 50%, maybe 100%. Adding 5 lanes will improve the performance by 500%. Not that I'm all that much in favor of adding lanes. Probably should reduce the number of cars, but it's a different discussion altogether. It's going to go to a different example. We have a very old till, and there's the more electronic format, but if our supermarket really wants to process large numbers of customers, we have to go parallel. It works in real life, and the same applies to our application systems. So, if you have to do it at all, that's too bad. Don't do it more often than required, and if you're going to do it, don't do it on your own. If there's opportunity to parallelize. Is that a word? It is? Okay, good. Sorry? Yeah, that's great. You know Moore's law, the capacity, the processing power improves by a factor of 2 every so many years, I'm not quite sure what it is. We have reached a point where the physical limitations of our CPUs are reached. There's only so small you can go. The atom has a certain size, it stops somewhere, but we can still improve performance by adding cores. So now the speed of CPUs, the speed of our processing units, are improved by adding cores and doing things in parallel. Those cores are processing in parallel. That's something that eventually we probably will have to deal with, although Java is pretty good at dealing with that already. That's not the level at which we're going to discuss it. I won't go through every single bullet on the slide. The slides are available, and afterwards you can look at various options for parallelizing things. Again, it's something that you can do at every tier. Not as well on every tier as on the next tier, so not very good in the browser tier, but pretty good, of course, in the application server. And also most databases will perform a substantial degree of doing things in parallel. When you're going to do things in parallel, you do have to bear in mind a number of things. In this case, we have this pretty lady operating a coffee machine, and she's pretty popular given the long line that's there. Now maybe we could hire 4 more pretty ladies, and a pretty guy maybe as well, to shorten the line. But it wouldn't help us. In fact, the line would get longer. These 5 people would be in each other's way, but there's still only one coffee machine. That's the real bottleneck here. So we should probably add both people to serve and machines to brew the coffee. At some point, like I said, I'm also a bit from the other side, from the Oracle side, the database side. In the database, we could keep on improving the ability to do parallel processing, use the parallel capabilities of the CPU, and keep on improving the degree of parallelism in the database. And we found out the performance actually got worse. problem was, performance of the database wasn't constrained by the CPU, it was constrained by the I/O operations. And if you start parallelizing the CPU, even more processing threads will try to get access to the data on the disk. So it's like the coffee machine. They're all trying to use the same coffee machine, the same I/O channels, and eventually it will get worse. You don't get improvement. So you have to parallelize in a smart way. A place where they didn't parallelize in a smart way, or at least. I was at the Hilton last Friday, and we were in a fairly long line, I think about 50 or 60 people, and there's only one lady doing the check-in. They had prepared for parallelism, but only by a single resource type, and they require 2 resource types. I had plenty of time to take a photograph. Like I said, you see it everywhere around. But the performance is something that you will experience in a web application. How fast do I get the response when I perform a certain action in my web page? We also have it at the level of the business process. In this case, we have a business process. It's something about a loan request. It starts with doing an identity check with a federal service. It's sort of a Dutch context. I'm not sure it applies around here. It's a very simple example, really. Then we do a bit of fraud analysis. We evaluate the request. Once we have established the identity and done our fraud analysis, then we either reject the request or transfer the money. The business process can take up to 6 days and 3 minutes. Not sure where the 3 minutes came from. That's because the first step could take up to 1 day, the second step can take up to 2 days, and the third step could take up to 3 days. How can we improve performance here? Well, I'm not going to go into the evaluation of the request. If that's a process that's programmed badly or that's performed wrongly, that's not what we're going to look at. We're still looking at it from very far away. It's this helicopter view. And let's first take a look at a different example. Oh, for your information, about 98% of the identity checks checks out okay, and about 99.99% of the fraud analysis cases indicates that there is no fraud. Another example. That dinner is taking mighty long. We've got 4 people sitting around the table, dinner is served, at the end they're all satisfied, but it takes up to 3 hours and how there, again, 3 minutes. That's pretty long. Why is it taking so long? Let's take a look at how the process of the dinner is implemented. We've got John, we've got Mary, we've got Daisy, and we've got Marty. And this is how you could describe the process. They eat soup, they eat the main course, and they eat dessert, or at least 2 of them eat dessert. Why would it take so long? Well, it's a sequential process. First, one person eats soup, and only when he's done, the second person starts eating soup. It's a bit ridiculous, isn't it? Well, we could redesign, or not, it's not necessarily redesigning, revisualizing the process like this. It's exactly the same process, it's still completely sequential, but we're only rearranging a few lines. There we go. Now all of a sudden it's a parallel process. They eat soup at the same time, they eat their main course at the same time, and eat dessert at the same time, and we've gone from 3 hours and 3 minutes to 1 hour and 3 minutes. Now that's more like your American dining speed. Check, please. Could even get a little bit better, if not more refined. Instead of waiting for all of us to finish our soups or waiting for all of the people to finish the main, you could also just eat your soup, then eat your main and be done with it. And then we get down to 53 minutes. Back to the loan request. Turns out that on closer inspection, the different steps in this business process are not related. We're not using the result of the identity check for the fraud analysis. We are not using the outcome of both the identity check and the fraud analysis to evaluate the request. Of course, if either the identity check fails or the fraud analysis indicates that it's a fraud, we don't have to evaluate the request. But since it happens only in very few cases, we might as well assume that it's a valid request and perform the evaluation. So if you now turn this business process in a parallel one, what we get is, well, it's in parallel max 1 day, max 2 days, max 3 days, and the 3 minutes, of course. And now we're down to 3 days rather than 6. Just by taking a closer look. I was actually at a customer 3 weeks ago, different one than the one I was thanking from the bottom of my heart. This one was nice too. At the moment, all their documents are paper documents, are hard copy documents. It's the Dutch court system, and whenever a new case is brought on, the expression you would use, a new case is initiated, some documents are created or are received, and they travel from desk to desk. Now we are thinking about digitalizing all documents, and we have tremendous opportunity then to redesign the business process. Because there's only a single hard copy of every document, the process now needs to be sequential. The documents go from desk to desk, and there's only one document at any given time. But once the documents are in digital format, multiple people can be working with the documents at the same time. So I proposed this to the organization, that we can really speed up your process if we start doing things in parallel. I said, well, you know, for now, we have this folder that holds the hard copies of the documents, and this folder goes from desk to desk. We are now taking out the hard copies of the documents. They're going to go into a content repository, but this folder will still go from desk to desk, because that's the way we organize our process. And on the folder, on the outside of the folder, it says it now has to go to this person to perform this task. So for now, we're not going to change the process, only change the way the documents are handled. Sometimes you may feel as though you can't do things in parallel. It's a Dutch custom to eat pancakes, especially at children's parties. So with pancakes, you sort of have 3 stages. You have to prepare the batter, you have to bake the pancakes, and they will be eaten. Can we do things in parallel? Well, batter, bake, eat. You have to first bake them before you can eat them. You have to first make the batter before you can bake them. So can you do things in parallel? Well, you could ask for a second pan. You could at least bake in parallel. But actually, you can make a much larger improvement if you think about and something I would call pipelining. It's almost like a conveyor belt. Once the first pancake has been eaten, one of the children can start eating. Sorry, has been baked, one of the children can start eating. So instead of baking the entire stack of pancakes and only then starting to eat, it's much better, or at least if you want to get the children out of your house as quickly as possible, it's much better to bake a pancake, give it to a child, bake the next one, give it to the next child, and do it like that. So instead of waiting for the entire activity to complete before starting the next activity, pipelining is a concept that would suggest that you hand part of the result of one activity to the next activity while continuing producing the other results. Fairly obvious when it comes to pancakes. Actually is not all that hard to implement in your applications as well. So for example, in the Oracle database, which is my home ground, there's a concept called pipeline table function that really allows you to perform a query against a table. The results of this query are still being fetched from the database, but the first rows are already handed over to some PL SQL, some stored procedure that can start processing them, that could even hand them to a next process or to the client requesting the data. So you will have this line of, at far end, the process is still fetching rows. At the second station, the first rows are being processed. At the next station, the rows that have been processed are being further processed, etc. So you have this horizontal parallelism. I'm not sure if that's a way to describe it, but you can probably imagine that if you don't wait for activity to completely complete, for the results to be complete, but instead start processing one of the results if the results themselves are independent. It doesn't work always, but frequently it may help you out, and it can be done within a tier. It could also be done across tiers. So for example, in your application server tier, you could start processing data, and once you have processed the first piece of data that might make sense to the client, you could use a WebSocket, for example, to send the information or to push the information out to the client. When talking about performance, it really all boils down to this guy. And it may look a little bit differently on different operating systems, but in the end, it's whenever the hourglass appears, the user can't work. That's where the experience of bad performance kicks in. Why do we actually show the hourglass? On many occasions, we may not really have to. For example, it's a printer. Probably recognize the beast. If a user in an application requests a document to be printed, we probably should not do this as a synchronous job. Tell the printer to start printing, wait for the printer to let us know that the document is complete, and then tell the user, well, the document has been printed, you may continue. That would result in a user complaining about bad performance. There's no reason for the user, for the application, to wait for the printer to finish. It's more like the job has been submitted. It's a fire and forget action, and the user can be informed that the job has been started, and the user will typically accept that. He or she knows that at some point he or she has to go to the printer to get his or her document. This PC thing is tiring. So instead of doing synchronously and making the user, the application, and the user wait for it, you frequently can improve the perceived performance tremendously. You haven't actually sped up anything, but the perception of it is much better. So as part of the it's staring you right in the face approach, there might be a situation where you don't have to do things immediately, synchronously, having the user wait for an operation to not only start, but also complete. And again, that's something that you will see in the real world as well. Looking at our application architecture and the different mechanisms that we have at our disposal to implement this, in many cases we can just submit information and we don't have to wait for the result. We've got asynchronous web services, we got JMS queues. We have the option to, even though data in the end should be persisted to the database, there should be a database transaction to really persist the data. One of the ideas in NoSQL is that we persist it to a grid that's distributed across multiple tiers that's thereby safe, and use a write behind asynchronously, detached from the application, to actually commit the data in the database. So we can decouple the operation to receive the data from the application, ensure that it's safe, and then persist later on, asynchronously. The database itself also has a mechanism like that. Well, actually, this is a different one. At the database level, you can define constraints. You're probably familiar with them. You've got primary key constraints, unique key constraints, foreign key constraints, and in many databases, other constraints like check constraints as well. And typically, these constraints are enforced at the statement level, and as soon as a row has been found to violate a constraint, the statement will fail. That's the way it usually is set up. If you're doing a large batch operation, and in a moment I'm going to argue against batch operation, but if you're going to do batch operations anyway, you might be updating many, many rows. It could be 100,000, could be 1 million. Now suppose that this is taking place during the night. In the morning he comes into the office and turns out that on the 900,000, 99,000, I'm not going to complete this, 825th row, the validation failed and the entire transaction was rolled back. That would be a pity. Especially since you probably would have wanted this transaction to complete for all the rows except the one where it failed. Well, in the Oracle database, I don't know about other databases, but it may have a similar mechanism. There's the option that's called the DML error log, where you can indicate if I perform a DML operation against this table, and no more than X number of rows violate the constraint, then go ahead and complete the statement, and all the rows that violate the constraint should be written to a separate table so I can inspect them and decide what to do with them. Just a mechanism that might be handy to know, though of course it's more up to the database administrator. But don't use batches. Maybe that's too broad a statement. Many of the batches in our systems are there because they are there. If you ask the people responsible for a system, why are you doing this in a batch? They will either say, well, it was always done in a batch, or they say something like, we don't have enough resources to do it online. And that used to be true 20 years ago, or maybe even 10 years ago. But the processing power that we can throw at our application and the activities it needs to perform has increased so tremendously that many things that really had to be done in batch in the past may very well be possible to do online, maybe not synchronously, but at least asynchronously near real time right now. So you should revisit batches, especially when those batches can put a peak load on a system. And we used to have these night windows, but we are increasingly working in 24/7 operations, so you don't really have this night window. That's the reason why you would like to get rid of the batch. But it's frequently no longer necessary to have a batch. For example, to do data replication. Data is changed in one database, another database should be updated as a result. Now we batch it up, and during the night we will update the other database. Well, that means that for 12 hours, or on average 12 hours, we have data that's out of date, or that's not already there. I was at a customer 2 years ago, and it's actually true. When the marketing people needed to have the latest customer information, they were working in a different database than a database that actually contained the customer information. They had to submit a request and wait for 4 hours before the batch job was being run, during the day, by the way, to transfer all the information that was required to the other database. Completely stupid, but a leftover from a time long ago. So revisit your batches. I can't say that any batch is bad, but many batches are not really necessary any longer. Well, you probably know this one. Don't call us, we'll call you. I've got children, and sometimes they're waiting for something. My youngest recently had his birthday, received some coupon for a web shop, and he decided to buy a keyboard. A $20 keyboard, not really high quality. In fact, when he received it, he broke it right away, but that's a different story. And he had ordered this keyboard over the web, largely by himself. And then every day after ordering it, he asked, is it already here? Is it already here? Daddy, has the keyboard arrived? He asked it every day. And then after 6 or 7 days, he stopped asking. Then it arrived. I forgot all about it. And only 3 days later, oh, your keyboard has arrived. That's not really true. It's a way to explain this. Well, the first part is true. He kept on asking for it. But he really kept on asking for it. In an application, an end user may be interested to learn about the latest data. And in most web applications, to learn about the latest data, you press F5. And you'll press 5 again. When you're expecting new information, you'll keep on pressing F5. You're constantly calling to ask, has my keyboard arrived? Get my latest information. Some systems can experience quite a load because of this. If it's not handled well, if you don't detect that the question has been asked already, sounds like never mind, different association. If you keep on asking the question, and eventually you may stop asking the question or decreasing the frequency with which you ask the question, you may actually not get the information at the moment it becomes available because you stopped asking for it, or at least you didn't ask it right after it arrived on the server. So let's reverse it. Let's express an interest. Daddy, can you please tell me the moment my keyboard arrives? Okay, son, that's okay. I will. He doesn't ask. Keyboard arrives. I tell him. He didn't bother me. He received the information the moment it became available. Everybody's happy. The same applies to our system. If we can use push to inform any system or any user that has an interest in certain data, thereby we prevent the load we would otherwise be experiencing from the user constantly asking for the information, and the user would get the information the moment it becomes available. Well, one of the main themes during this Java 1 conference, of course, is the ability to use WebSockets, HTML5 in combination with WebSockets. That's one of the tiers, or one of the bridges between tiers where you could do push. There's actually more. So in our list of staring you right in the face, don't do things necessarily per request, or at least not per constant request. Express your interest once and then push the information once it becomes available. You will get the most up-to-date information. You will decrease the load on the back-end system. That's really what you're gaining here. I have to move on here. It seems like, are we out of time? A few more minutes? 3 more minutes. Some challenge. Don't bite off more than you can chew or than you have to chew. I've seen many web applications that have several areas. Tabs, maybe a tree with many nodes that may have been expanded but frequently are still collapsed. All these pieces on the web page have information associated with them. But as long as these pieces are not expanded, are not exposed, are not navigated to, we don't actually need the information. It's not yet shown. So why should we take the burden of collecting all the information before making the page available to our end user if the end user doesn't need it right away? We can do a post-load fetch of the data, either immediately after the initial load of the page is complete, or when the user expands a certain item. Depends really on how much data is needed, and if it's needed most of the times or only some of the times. But don't always just fetch all the data that may be required. It will have the user wait for much longer than really is necessary. So don't do it in 2 big steps or 2 small steps. 2 big steps would be to get it all at once, even though it may not be immediately required. There are some examples on the slide. 2 small steps, that's the example that I thank this customer for from the bottom of my heart. It's a pension fund, and they have this simple data model. They do pensions for multiple employers, and all of these employers have participants in some pension scheme, and each participant will have multiple elements in this pension scheme depending on the jobs they've had and the salaries that were associated with these jobs. So from one day to another day they would have been in a certain job with a certain salary, etc. That's all part of the information stored. And this information is presented on a web page, a single employer, multiple participants, and when we select a certain participant, we'll see the jobs and benefit details for a certain participant. Fair enough. They've done this using an object relational mapping framework, and what you get is a single query to fetch the employer, a single query to fetch the participants that work for this employer, or that have worked for this employer, and whenever we select a participant, another query to fetch all the benefits. And you see an indication of the numbers of records involved. One record, several hundreds of records, and tens of records. Now they use the same entities, the same mapping situation set up for doing a report. So you get many employers with all their participants, and for each participant all the jobs and benefits. What you see is the same queries, and the problem is not in the queries, the problem is not necessarily in the numbers of records. We now have several hundreds of employers, tens of thousands of participants, and hundreds of thousands of jobs and benefits entries, but it's fine. That's not huge numbers for your typical database. The problem is with the number of queries. It's like the shopping algorithm. We are going back and forth to the database for each participant and for each employer, but that's not really the problem. It's the participant. So in order to fetch about 100,000 rows, we'll perform 10,000 queries. The query is not a problem, but performing it 10,000 times to produce a report is a problem. So what can you do? Well, try to bulk it up. Try to tell the database, give me all these employers, give me all the participants for all these employers, give me the jobs and benefits for all these participants for all these employers. That's 3 queries. And then try to fit it all into your car. And perhaps your car isn't big enough and you have to do several round trips to the store. But even then, the total number of queries will be far smaller than currently is the case. Don't do it in 2 small steps, where it's like dialing an operator to request a telephone number and request it digit by digit. It's me again, the 3rd digit of the telephone number of this person, etc. Don't do things the hard way, obvious one. Don't do things in a convoluted way. And you have to look very closely. There's going to be a box on this monster truck, and this box is delivered, and the box turns out to contain a memory stick. This is not the way to do it. And sometimes we do it like this, only it doesn't look this obvious. So don't do it in a convoluted way. Stay pragmatic. If you don't think out of the box, if you don't step back to reassess the way you've been doing things, if you always follow the same approach that you may have followed in the past or that you may have learned from standards that are not necessarily flexible, then you may be doing things in a very convoluted way. And there's a number of examples on the slide. Not a good idea. The single printer we have in our office, and someone is printing birthday invitations for his dog. And we need his resource for sending out invoices. Very important, but our bottleneck resource is being held by some suboptimal, non-critical process. So don't do things in a suboptimal place, which really means don't use an important resource for an unimportant process. There are ways of dealing with your resources, handling your resources. I'm getting out of time here, so I have to rush on. One example would be, in the past we used to render HTML on the application server. We don't do that as frequently as we used to. We now do much more dynamic HTML rendering in the browser and only doing JSON-based data exchange with the server, because the only thing really that changes is the data. This is a good example of doing things in the right place, using the processing power of the browser and don't wasting both the processing power of the application server and the network for sending HTML, which is not really a very compact format at all. Don't perform a task in a resource that's not really up to an enterprise level job. That's what I'm saying here. And here are some examples, and one of the discussions I'm frequently having, again, being of the other side as well, is what you do in the database and what you do in the middle tier. I've seen organizations that implemented unique key constraints in the middle tier. I don't consider that a good practice. Database has been optimized for it far better than you ever could. And you are bringing data from the database to the middle tier that you don't really need there. And maybe your database vendor independent, but that's really not a big deal anymore. So there's the entire list. Don't do it if you have to. Don't do it under these other circumstances. When you architect for performance and you take this list into consideration, there's a number of features that you may want to at least think about applying to your application, to your architecture. It's far too hard to read in the back, so if you're interested, please take a look at the slides. They are available for download from SlideShare. They will be available for download from the Java 1 website. It gives you an indication of various mechanisms that you may want to use in order to address performance along one of the dimensions I mentioned in this presentation. And you see an overview of which mechanisms go with which parts of the it's steering you in the phage approach. To wrap it up, you need to define performance. You need to define performance requirements. You typically should do it based on business requirements. Performance and availability are part of the same spectrum. When your availability is 0, your performance is 0. The other way around, if your performance is 0, then you are no longer available. Look at performance across the stack and look at where performance is really spoiled, where it's going down the toilet, if you like. Don't start tuning in a place that only makes up 1% of the entire processing time. And the number of it's steering you in the phase guidelines, don't do it if you don't have to, don't do it on your own, etc. So I hope this has been of some value to you, and at least thank you for sticking around till now. Sorry for being late.